Honey, come over here.
What's the problem?
I'm planning on tiling the entire surface of our dining table with this.
Honey, you've been watching too many interior design shows again.
Don't worry, honey. It'll be nice once it's finished, I promise.
So what do you need me for?
I can't figure out how many of these 1-inch tiles I'll need to cover the entire table surface.
Why don't you just overestimate and treat the table like a square table?
Are you sure? Remember, you're paying for this.
In that case, let's just underestimate.
That wouldn't do.
I know, but the area should be somewhere between our overestimate and our underestimate.
You have a point there.
Mom, Dad, I can't help but overhear arguments. Why don't you just calculate the surface area of the table in inches, since you're using 1-inch tiles? It's just the square of the radius of the table times pi.
Now, why didn't you think of that?
Why didn't you think of that? Oh, and Paolo? What's pi?
What is pi anyway?
It's a constant which is approximately 3.1416.
Yes, it is. But how do we get 3.1416?
Ma'am, if I remember right, it's the ratio between the circle's circumference and its diameter.
Is it really? Let's find out, shall we? I have here several canisters of various circumferences and radii. I'd like you to measure the diameter and circumference of each and write your findings on the board.
Let's see. This one has a circumference of 7.8 inches and a diameter of 2.5 inches.
Let me try. This one has a circumference of 8.75 inches, while it has 2.75 inches as diameter.
I'll take the last one.
This one has a circumference of 9.5 inches and a diameter of 3 inches.
Hey look! The ratios are all approximations of pi.
It's quite easy to measure the circumference of a circle if the circle were part of a cylinder. But what if the circle is on paper or on this board? How would you measure its circumference then?
We could drive the nails into the board to hold the tape measure in place.
We could, but there are two things about your suggestion that is flawed. First, we'll get into trouble. Second, if we do manage to put nails on the board and wound the tape measure about them, you'll simply be measuring the perimeter of a polygon, not the circumference of the circle. Not with our tools, but
I know! We can inscribe a polygon within the circle with as many sides as physically possible.
Oh, I see. So the perimeter of your n-sided polygon will be an approximation of the circumference of the circle.
But wouldn't that be an underestimate of the circumference?
yes, that would be an underestimate of the circumference.
Let's do what the couple in the video were proposing.
What? that?
Let's overestimate the circumference by circumscribing the same n-sided polygon on the circle. The average ratio should give us a good approximation of pi.
Good idea! Let's try something simple, like a regular hexagon. You can follow what I'm about to do on your seats. Let's start off with any circle. The radius of a circle can be struck exactly 6 times around the circle. Connecting each successive intersection produces a hexagon. Next, let's describe a circle in the hexagon we just drew. Let's now construct a smaller inscribed hexagon upon the smaller circle. Get rid of the larger circle so we won't get confused. Note that the perimeter of the smaller hexagon will be an underestimate of the circumference of the circle, while the perimeter of the larger hexagon will be an overestimate of the circumference of the circle. Let's now measure the diameter of the circle and the perimeters of the two hexagons. Can I have any volunteer?
I'll do it, ma'am. Let's see. The circle has a diameter of 8 units. The larger hexagon has one side that is 4.4 units, which gives us a perimeter of 26.4 units, while the smaller hexagon has one side that is 4 units, which gives us a perimeter of 24 units.
Thanks, Alaya. Now, what's the ratio between the perimeter of the larger hexagon and the diameter of the circle?
It's 3.3.
And how about the ratio between the perimeter of the smaller hexagon and the diameter of the circle?
That one's 3.
Ma'am, does that mean that pi should be somewhere between 3.3 and 3?
Well, isn't 3.1415 somewhere between 3.3 and 3?
Oh yeah! Oh, and the average of 3.3 and 3 is 3.15, which isn't pi, but close to it.
That's a very good observation, Maurice. Now imagine having a polygon with more sides.
We'll get a better approximation of pi.
That's right. So let's try another polygon, something with more sides.
Ma'am, why don't we double it this time? Let's have 12 sides.
That's a dodecagon. But how do we do that?
We start out like what we did with the hexagon and simply find the midpoint of each arc between each mark. Does anyone have any idea how we can do this?
I think I have an idea. Let's extend each mark to the center of the circle and construct angle bisectors out of each angle formed.
Do you remember how to do that?
Yup, let's consider this angle for example. The first task is to draw an arc centered at the vertex of the angle. Fortunately, we already have one.
Where?
The circle, of course. Let's label the points where the arc intersects the angle as P and Q. So all we need to do is to draw two arcs that have the same radius, each centered at P and Q. And arcs must be large enough to intersect. We'll call the intersection X. Finally, we draw a line passing through the x and the vertex of the angle. And where this line intersects the circle will be a vertex of our dodecagon.
Will you do the rest?
Sure, ma'am.
Now, we need to inscribe a circle in the dodecagon and inscribe the smaller circle in the other dodecagon. Any volunteers?
I'll do it.
While you're at it, why don't you find the diameter of the circle and the perimeters of the two dodecagons?
Yes, ma'am.
So, the diameter is 8 units. The smaller dodecagon has one side measuring 2.05 units. That makes the perimeter 24.6 units. The larger dodecagon has one side measuring 2.13 units, which makes its perimeter 25.56. So, based on three measurements, pi will be between 3.075 and 3.195. Hey, that's much smaller range than the last one.
That's right! Using hexagons, we found pi to be approximately 3.15. Using the decagons, we found pi to be approximately 3.135, which is a closer approximation.
So, the more sides, the better?
That's right! And that is exactly what Archimedes did around 250 BC. He actually used a 96-sided polygon.
So pi is approximately 3.1416.
Yes, teacher.
What are you two doing?
Excuse me, but do you know who you're talking to?
Don't mind them. As I was saying before, math sure was interesting today.
Yup, we learned how to define pi and derive pi using geometric constructions. You two better get dressed for PE. Nice.
Don't worry, we came prepared.
Oh.